Welcome to Module 3. In this module, we're going to use the instrument for the testing of unknown samples, just as you will for your applications. Although we cannot practically expect to demonstrate every type of grade or alloy you may encounter, we will measure several typical examples of alloys that represent the popular grades in use today. The measurement procedures and evaluation of results will be similar, even if your particular alloy grades may be different. If you do have unique needs that are not covered by this module, please refer to the user's guide or contact your local Thermo Scientific Niton Analyzers sales representative for assistance.
We'll assume you just completed Module 2 and have verified that the instrument is functioning properly. Since the Niton XL3 always defaults to the last analytical mode used to take a measurement, all you need to do is select the test icon and proceed to measure samples. For measuring in the more specialized alloy modes, such as signature match, superchem, or pass-fail modes, please refer to your user's guide or contact your local sales representative.
The all-alloy mode is used predominantly for alloy grade determination with chemistry. This mode is used by all types of industries for all of the various types of metal alloy families that can be tested with your Thermo Scientific Niton analyzer. Our alloy analyzer customers range from the metal mining industries, to alloy producers, to alloy distributors, and to users such as aerospace companies, inspection companies, government agencies, and ultimately to the metal scrap recyclers.
Let's begin with a niobium stabilized version of stainless steel 304, called stainless steel 347, an austenitic stainless also known as chrome nickel stainless steel. We'll test it as though it is an unknown sample, but later we'll compare the measured results to the certified values. This will help to demonstrate that your handheld Niton analyzer truly does provide you with lab quality accuracy for alloys.
We place the analyzer measurement window on the alloy sample and then pull and hold the trigger for typically about 5 seconds. The results will continue to become more precise, as demonstrated by the steadily decreasing values in our 2 sigma error column as we measure for longer periods of time. At the conclusion of the measurement, we release the trigger and the final calculation is displayed.
The grade identification, or ID, of the sample is automatically determined by the instrument. It compares each analyzed alloying element value to a library of over 400 alloy grades in a grade table stored in the instrument's memory. Each alloy grade has a lower and an upper limit set for the range of allowable variance in the specification or recipe for that alloy. These limits are industry standard values, and most, but not all, are based on the Unified Numbering System, or UNS specification for the alloy.
Whenever a plus sign is on the screen, it indicates that more information is available. By tapping the plus sign in the readout next to the sample ID, we display the library minimum and maximum values along with our measured values for the alloying content of the identified alloy, stainless steel 347. We may use the up-down scroll arrows to view all elements in the table. By tapping the Help button on this screen, we see the key to colors of the measured values. A measured value displayed in black indicates the calculated element content is within spec for the alloy. A red color indicates the result is out of spec. Blue implies a tramp element or an element that is not specified but has been detected. Brown means the result is below the limit of detection, or LOD. Increasing the test time will improve the detection limit for every element.
Note that the sample name, or grade ID display, is followed by the quality of match, or confidence number, in this case a 1.2. This number can range from 0 to 10, with 0 being a perfect match and 10 being a distant no match. A no match will occur when the calculated confidence number goes over a factory default value of 4. For matched alloys, values between 0 and 4 show the degree to which a sample's makeup differs from the mid-range of the alloy grade's chemical content specification. Between 0 and 2 implies a good match, 2 to 4 a probable or possible match, and more than 4 a no match.
An asterisk will appear next to any elements that are out of spec in reference to the min-max values entered for that particular element in the grade library entry. Since alloy producers will typically use the minimum allowable amount of expensive elements in any alloy recipe and the maximum amount for inexpensive alloying elements, don't expect all alloying elements to fall in the mid-range when you test a sample. In other words, don't expect a match number of 0 very often. Remember, the match number is based on comparison to the standard UNS alloy specifications in most cases.
Now, let's look at our test results for this measurement. Note that the left-hand column contains the element symbol, the middle column shows the concentration result, and the right-hand column indicates the 2 sigma standard deviation, also called error or precision, of the measured concentration. This 2 sigma value represents 95% confidence that the calculated values will be within the lower and upper limits set by the 2 sigma boundary values. 95% confidence implies that if this same measurement was taken 100 times on the same sample for the same length of time, 95 times out of 100, the measured chrome concentration would fall between 17.03 and 17.79%. This error value is taken into account in calculating the ID confidence number.
Another example is the value for nickel. Note that the analyzed value is 8.92% and the precision of measurement is plus or minus 0.45%. Similarly, molybdenum, or moly for short, shows both analyzed concentration and calculated precision values. It is so important to be aware of the precision of each measurement that I often tell new users that no concentration number has any quantitative meaning until we know the associated error.
Now let's look at the effective analysis time. Instead of holding the trigger for 5 seconds as in the last measurement, I'm going to perform a 20-second test. What you will see is a 2-fold improvement in the precision of every element. In other words, the error will be cut in half. The rule of thumb that we are demonstrating here is that the precision doubles for each 4-fold increase in measuring time. Okay, let's compare the values for the 2 shots. Here we see the chrome for the 20-second shot is at 0.18%, and for the previous 5-second shot at 0.38%, or about double the precision for the longer measurement. The same will be true for nickel, moly, and iron.
The Niton analyzer has so much greater accuracy and precision than the allowable tolerance in the typical alloying min-max specs that the small amount of error associated with a 5-second test is almost always sufficiently accurate for a 100% confident ID. However, for comparing chemistries to a certified value, we suggest using 20 seconds or more of measuring time. We can see the reason for this by comparing the certified values for this stainless steel 347 standard to the calculated values based on the analysis results shown here. I'll read the certified values while we view the analyzed values for both the 5 and 20-second shots. Moly, 0.5%. Nickel, 9.06%. Manganese, 1.43%. Chrome, 17.61%. Niobium, 0.63%. And iron is the balance element. Clearly, the 20-second test is more precise and therefore has higher confidence in the displayed value and statistically better results. Most chrome moly, stainless steel, and nickel or titanium-based alloys need little or no sample preparation when the surface is seen to be clean. However, because XRF is a surface-sensitive technique, it's important that the surface be both clean and representative of the alloy. For accurate results, it's absolutely necessary to remove any non-representative surfaces, such as paint, rust, scale, zinc coatings or platings, or any non-representative alloy surface. The surface measured must always be the intended target material. Whatever's on the surface is what the instrument will measure. A portable grinder we've found to be both small and useful for field work is the Makita 9500. You can find that on makita.com. A more powerful but larger portable grinder is the DeWalt DC-10KA, shown here, which can be found at dwalt.com.
Remember also to select an appropriate abrasive. Don't use zirconium oxide grinding paper if you are analyzing for minor amounts of zirconium, like with some aluminum alloys, 7050 for example. Some light elements in alloys like magnesium, aluminum, silicone, and phosphorus, and sulfur can't be determined without the use of the high-performance model, the Niton XL3T S900, equipped with gold technology. When using the XL3T gold instrument, don't use an aluminum oxide grinding paper on an alloy that will be analyzed for low levels of aluminum alloy elements, or silicon oxide grinding paper when low amounts of silicon alloying elements are to be determined. And please, be sure to wear all appropriate personal protective equipment and follow the manufacturer's safety instructions when operating your grinder.
Okay, now let's test a typical petrochemical alloy, a so-called chrome moly steel, such as the 5-chrome half moly. Many refinery pipelines are constructed using this alloy. Typically, the primary goal of the testing in a refinery is to verify the correct alloy grade, so we'll measure for just 5 seconds. Note that the ID is obtained long before the 5 seconds has elapsed, assuring the technician that the analysis is routine and the results can be reported with high confidence. Remember that many 5-chrome process pipes are zinc-coated, and that this coating must be removed in order to obtain the correct ID in chemistry. In such cases, be sure to obtain any required approvals to grind the surface down to the clean, bare alloy metal.
An example of a more challenging analysis would be the testing of the nearly twin alloys 304 and 321 stainless steel. These two alloys have overlapping specification ranges for all measurable elements, with the exception of a fraction of a % difference in titanium content. Titanium is added to 321 as a stabilizer for welding and for avoiding stress corrosion cracking with certain corrosive chemical environments. The petrochemical industry must be able to accomplish this difficult alloy separation in order to have absolute confidence that the correct alloy grade is applied to the intended use.
Here, for example, is a 321 titanium stabilized stainless steel that we will test. When only 321 is displayed for a few seconds, we can stop the test and document the grade ID. The same will be true for the other nearly twin alloy stainless steel 304, which has no titanium added. Of course, a zero concentration level is harder to quantify than even a fraction of a %, so it may take slightly longer to drop the second choice, 321, in the case of 304 analysis. A useful accessory for benchtop testing of small parts is the XL3T Smart Stand, portable test stand. We will utilize this stand for safety with undersized samples in our following demonstration. To set up the stand, place the folded stand on your benchtop with the scissored legs down. Next, lift up the top part of the test stand. As you do so, the scissored legs will rise up and come together. Hook the bar in the notch in the back of the test stand. Use the included communication cable to attach the smart stand to your analyzer. Insert one end of the cable into the COM port on your smart stand and the other end to the appropriate port on your instrument. By connecting the smart stand, your analyzer knows whether the protective lid is open or closed, and thus whether it is safe to initiate a test. Plug the USB cable into your computer's open USB port. Plug the other end into the smart stand's USB port. The smart stand will draw the operating power that it needs from your computer.
The Thermo Scientific Niton analyzer is smart enough to deal with almost every situation, but there will be a few examples of alloys that cannot be handled without interpreting the analyzer data based on knowledge of alloys. For this reason, we will measure several types, shapes, and sizes of alloys to demonstrate the use of the analyzer for this application. We will start with some tough examples. Here is a 2mm 316 stainless steel wire. As we can see, After only a brief test, this undersized sample is correctly called as a 316 stainless steel. The analyzer will compensate for undersized samples down to about 1 millimeter.
So how about a thin foil? This copper alloy foil is a good example of a very thin foil. It's a CDA 260 cartridge brass. It's about 0.2 millimeters thick. Note that again the analyzer has compensated for this thin sample, and it correctly identifies the alloy and provides its chemistry. This correct call will be the case for thin samples down to about 0.1 millimeter thickness, assuming they cover the entire measuring window.
Now let's demonstrate an example of an incorrect measurement procedure. Instead of measuring the 316 wire in the test stand as before, let's shoot it on the table. Since the measurement area is 10 millimeters squared, and this area is not completely covered by the alloy under the test, we are therefore inadvertently including the surface of the table in our analysis. With the table being added to the wire analysis, we obtain a puzzling result. Note that the light matrix or material content of the table has activated the aluminum algorithm in the instrument software. This is due to the high backscatter from all light matrices. For this reason, when we are not using a test stand, we must disable the aluminum to measure samples that are smaller in size than the 10 millimeter square measuring aperture. The ideal means of testing these small samples outside of the test stand is to place them on a minimum of ½ thick sheet or block of pure aluminum with the disable aluminum function activated on the instrument. This example is a pure aluminum Series 1000 sample block. When we measure the same 316 sample placed on this block with aluminum disabled, we now obtain the correct result.
As we said previously, the instrument operator must be alert and able to make good judgments in cases where the sample is not clearly representative at the measurement surface, or it cannot be fully analyzed for all alloying elements. Some surface coatings are not obvious because they are similar in color to the alloy. Examples are silver or cadmium metal coatings that might look like the alloy itself. Some examples of the need for a judgment call on the part of the operator will be given next.
Here is a sample of a bolt that when measured initially reads a mixture of steel and zinc. This is a material that has a zinc coating. Notice if I measure at the end of the screw where I have ground the surface, the reading for zinc drops dramatically. Since some of the signal is still received from the non-ground areas of the bolt, we still note some small zinc reading. The alert operator will know that the steel alloys don't contain zinc. Therefore, the conclusion is that it must be coated and we should grind the sample prior to its analysis. We can also notice a slightly off-color yellowish tint to the coated area that is not typical of a clean steel surface.
Any iron or steel containing only carbon as the alloying element will be identified as iron/carbon steel to indicate that we cannot test for carbon and therefore do not distinguish between pure iron and steel with carbon content.
Let's talk about normalization. The reason the instrument is smart enough to correctly measure samples of all shapes and sizes, including undersized samples, is that it automatically performs what is called normalization on every reading. This means we force the analyzer to total all detected elements to 100%. When measuring undersized parts, the signal is reduced for all elements proportionately, and we can therefore use the ratio of the measured elements to normalize the result to 100%. Of course, for reasons we just mentioned, it can only do this for representative surfaces.
However, this huge benefit has one minor drawback. A small percentage of alloys may contain significant amounts of non-detectable elements. 138MO, for example, which contains 1.5% aluminum, or Z-core, which contains about 6% silicon. In these cases, the instrument will normalize to 100%. So, if we have a stainless steel alloy with the alloying content comprised of non-detectable elements, such as 6% silicon, the reading for all elements except silicon will be normalized to 100%, therefore causing a 6% high bias distributed proportionately across the detected elements.
To correct for this bias, your Niton analyzer provides a feature called Light Element Correction, or LEC. LEC will correct for any non-measured element in an identified alloy based on the SMART library in the instrument. This means that alloys that contain large amounts of carbon can indicate that carbon ought to be present according to the alloy grade specification. With this new gold technology, light elements such as silicon in this Z-core sample can be determined directly. Since we are using the standard technology, we cannot measure these light elements: magnesium, aluminum, silicon, phosphorus, and sulfur.
Let's turn the LEC off to demonstrate the problem when the LEC feature is not activated. An example is the measurement of Z-core, which is a stainless steel, somewhat similar to 316 stainless steel, except it has 6% silicon content to help survive longer in high sulfur environments. Without either a helium purge or a gold technology, contact your representative for details, silicon cannot be detected. Therefore, all the other elements are determined and the alloy is forced to read normalized, value of 100%, for those remaining elements, minus the silicon, which is added to the other elements proportionately.
Let's now switch the LEC back on and see the difference in results. Here we see the detected alloying content values have now been reduced to their correct levels, and the LEC is displayed as 6%. This is a more exact reading for this alloy because it is corrected by the nominal 6% value of the non-detected element, silicon. Note that if the alloy is not in the instrument's grade library, the LEC cannot be corrected for or displayed.
Other modes such as precious metals, mining, environmental, ROS, restriction of hazardous substances, and consumer products can be installed on your analyzer. Measurement procedures and the evaluation of results will be similar to what we have shown for the alloy mode. When in doubt, please refer to your user's guide or contact your local representatives.
This is the end of Module 3. Module 4 will cover PMI, Positive Material Identification Application, and accessories.
Welcome to Module 4, PMI Training and Accessories. The requirement for positive material identification, PMI, of alloy materials in refinery systems and petrochemical plant operations has grown dramatically over the past 20 years. This requirement has been driven by the loss of plant equipment and production, along with loss of life, as a direct consequence of having the wrong material installed in a process plant. The new U.S. Occupational Safety and Health Administration, or OSHA, CPL 0300004, Petroleum Refinery Process Safety Management National Emphasis Program, is an example of the type of enforcement taking place worldwide as a result.
Let's talk about PMI best practices. The American Petroleum Institute, or API, has issued recommended practices called RP 578 as a guide to PMI best practices. This is at least partially in response to OSHA's implementation of the National Emphasis Program, placing the burden of documentation and training squarely on the shoulders of the refinery owners and operators. The API has previously published inspection codes for piping, API 570, pressure vessels, API 510, and storage tanks, API 653. More recently, API has approved an updated version of the API recommended practice, RP 578.
To certify or recertify API 578 inspectors in proper guidelines and application procedures utilizing XRF and optical emission spectroscopy, or OES, technologies from PMI, a 2-day course has been approved by the API. This course provides attendees with a thorough understanding of API RP 578 guidelines and procedures, as well as a practical hands-on experience with XRF and OES instruments. A third day of field testing is optional. More information on API RP 578 training is available at api578.com.
Given the record of serious accidents and deaths in the petrochemical industry, OSHA is also conducting on-site inspections in the United States to assure that we're following best practices in PMI testing. To complement this effort, in conjunction with Analytical Training Consultants, or ATC, we offer a 2-day API-approved certification course. Additionally, we have developed a comprehensive turnkey PMI testing program. These new developments in technology and training are making it easier to perform PMI in more locations with greater accuracy, with better trained operators than ever before. The complete Thermo Niton Analyzer's PMI alloy testing system includes the latest advancements in Niton analyzer capabilities, plus refinery-specific testing accessories that augment the use of XRF, as well as extending the reach of the technology.
Examples of the incremental capabilities include
Weld Spot, a collimator that narrows the X-ray focus to isolate welds from the base materials.
CamShot, an internal CCD camera to aid in analyzer positioning and to document sample location for traceability.
Direct Read Electronic Position Indicator, EPI, data logging buttons.
Real-time GPS integration. Bluetooth wireless portable printer for on-the-spot hard copy documentation of tests.
PMI Specific Certified Reference Materials, or CRMs. Hotfoot, high temp shielding for use in testing of hot materials up to 850 degrees Fahrenheit.
Extend-a-pole XRF extension pole to reach hot or difficult to access areas.
PMI Standard Operating Procedures, Best Practices and Procedures document.
API certified PMI training.
All specifically designed to provide complete assurance of data integrity under the most rigorous conditions encountered in our industry.
We will now go over the PMI kit and its use. The built-in weld spot provides small spot collimation for welds less than 8 mm in diameter. Weld spot focuses the X-ray excitation beam to a 3 mm spot size for isolation and analysis of welds or other small areas. Weld spot can be turned on or off depending on the application. The CamShot color CCD camera option always comes with weld spot. To use weld spot, select Test, then Tools. Under Tools, select Toggle Spot. To obtain optimum performance for routine PMI applications, be sure to deactivate this feature with the same toggle when your use of this feature is finished. The CamShot internal color CCD camera is integrated into the instrument for positioning of the analysis spot location on the sample and photo logging of sample analyses. To activate the camera view from Main Menu, tap the Common Setup icon, then Instrument Setup, then Hardware Setup. When this screen appears, select the camera box. A check mark will appear to indicate this mode is active. In the event you desire to save all camera images to the NDT file, select Save Image as well. To exit, select the Save button. Select Return twice to return to the main menu. When you enter the test mode, the camera image will appear on screen. The red circle indicates the focused 3 mm spot to be centered on the desired sample area.
An example of the benefit of this feature can be demonstrated by measuring this 3 mm fillet weld without the benefit of our 3 mm weld spot and CamShot options. Here we see the incorrect call on this weld since the 10 mm aperture takes in both the weld and the base material around the weld. Let's now activate the weld spot and CamShot features to allow us to easily isolate the 3 mm weld from the base material for testing. Here now is the reading taken with weld spot and CamShot activated.
We now see a correct call for the stainless steel 13-8 moly. When we test the base material, we see it as pure iron or carbon steel. Any iron or steel containing only carbon as the alloying element will be identified as iron, carbon, steel to indicate that we cannot test for carbon, and therefore do not distinguish between pure iron and steel with carbon content.
The electronic position indicator, or EPI, consists of the following components:
The EPI buttons for recording information,
the serial cable connector,
button link.
EPI button reader.
To use the EPI system, connect the cables to the button reader. The serial connector has 6 pins, and the button link connector has 4 pins. The button reader fingertip extension into the button reader's second receptacle as shown. Plug the gray serial cable into the button reader's top receptacle and into the serial connector of the Niton XL3 analyzer.
To set up the Niton analyzer for use with the button reader, you will need to go to Serial Output. From the main menu, tap the Common Setup icon, then the Serial Output icon. From this screen, tap Printer, which will activate the output to the button reader. The screen will now look like this, with Printer active and Live Serial Output grayed out.
The printer output settings determine what information is sent to the button reader after the Niton analyzer does a reading. From the main menu, tap the Common Setup icon, then Instrument Setup, then Miscellaneous Settings, and finally Printer Output. From this screen, you may select Print Less Than LOD, optional, not saved to button, Print Complete, optional, not saved to button, Print Data Fields, required, Print Date and Time, required. To initiate a measurement, press the button reader gauge key, which is the 0 enter key, to wait for data. This starts a 120-second countdown for data capture. Press the analyzer trigger to start the reading. After you have measured for a sufficient period of time, release the trigger. When the trigger is released, the data is sent to the button reader. You will hear a beep from the button reader, and Niton Reading will appear indicating it is now ready to write the data to the button. The first 3 lines of the data are shown on the display. At this point, you can use the up-down arrow keys to view all the data sent to the button reader. Using the fingertip probe, touch a button to write data to the EPI button. The reader will display CMB reading. To cancel the data capture mode, press the delete key until Niton Reading appears on the display.
The following screen shows what is stored on the button reader: the date and time, the sample number, the ID, the data entered into the data fields, including the example here, and the result information, including the element, percent, and error.
To delete records on the button reader, press the 5 key, which will show a pop-down menu. The delete key will close the menu. The enter will accept the menu choice. The up-down keys will change the menu choice.
For one-hand operation, it is recommended that you clip the button reader handheld onto the analyzer holster. You can easily press the gauge key to capture the analyzer data. Normally, you don't need to look at the display. Hearing the beep should be sufficient. Once you hear the beep, you are ready to write data to the button. A retractable lanyard makes the fingertip button probe easily accessible. Simply pull the fingertip probe and touch the button. The compressed data will automatically be written to the button. A good beep from the button reader handheld indicates all went well. For more information on the EPI system, contact your local Thermo Scientific Niton Analyzer's sales representative.
Also included in the complete PMI kit is a suite called the PMI 15 kit, which is a set of 15 refinery-specific Certified Reference Materials, CRM, alloy standards. These include common refinery alloys such as low alloy steels, the chrome moly steels, austenitic stainless steels, duplex stainless steels. These are useful for auditing and verifying analyzer performance.
Another option is a Bluetooth-equipped GPS for logging location coordinates into the EPI button. This can make relocating the buttons much easier. To use the wireless GPS with the Bluetooth-equipped Niton XRF analyzers, follow the Bluetooth connection instructions found in the user's manual to scan for and connect to a Bluetooth-enabled GPS device.
Once connected, the GPS unit sends out a number of signals that can be read. The analyzer will display the relevant information from the GPS after connection, as shown here. These coordinates can be viewed in the data screen in entry positions 8, 9, and 10. Scroll down to reach these fields. When the results are downloaded using the NDT software or EPI data button, the GPS coordinates are also downloaded.
You can also use Bluetooth barcode readers with your analyzer. There are two versions of wireless barcode readers, the scanner and the wand. Connect your barcode reader to your analyzer via Bluetooth, as described in your user's guide. Once the reader is connected, you can use it to input data into your analyzer.
On the data entry screen of your instrument, highlight the desired field. While pressing the button on the barcode wand, swipe the desired barcode. If the pencil successfully reads the barcode, it will beep. The barcode data will show up in the data field after the beep. There is a short delay while the information is being transmitted. You may also use the virtual keyboard screen to enter the barcode data. Please refer to your user's guide for more information on this accessory.
If you're planning to test materials that are at elevated temperatures, the following guidelines apply. Up to 400 degrees Fahrenheit or 204 degrees Celsius, no special considerations apply. In these cases, we recommend that you keep the measurement as short as possible, but consistent with good measurement practices. Typically, this means about 5 seconds, but no more than 10 seconds. If the temperature is above 400 degrees Fahrenheit or 204 degrees centigrade, place the analyzer into the hot foot jacket, which will allow operation with materials whose surface temperatures can be as high as 850 degrees Fahrenheit or 454 centigrade. When measuring samples at elevated temperatures, you must wear suitable protective equipment and follow all appropriate safety practices to minimize the risk of injury.
If access is difficult for the operator, the Extendipole accessory can be utilized. Place the handle of the Niton XL3 loosely inside the clamshell grip of the Extendipole. Plug the cable of the Extendipole into the remote trigger port. Make sure you plug it into the proper port on your analyzer, as shown here. Clamp the clamshell tightly around the handle of your Niton XL3.
Extension of the pole is accomplished by pressing in the button on the pole. Next, pull out the internal sliding pole until it is at the desired length. Then, snap the button into the nearest hole. You will also need to enable the remote trigger on your instrument by selecting the remote trigger checkbox on the hardware setup screen.
From the main menu, tap Common Setup, then Instrument Setup, then Hardware Setup. When this screen is displayed, click on the remote trigger checkbox to enable the Niton XL3 to interface properly with the Extendipole. You can operate your Niton XL3 through the trigger of the Extendipole as if it were the trigger of the Niton XL3. Using the Extendipole, you can test samples distant from a catwalk, high off the ground over your head, and in difficult-to-reach areas.
In addition to the world-class analyzers and hardware, we also provide world-class documentation and training. Documentation includes the user's guide for analyzer, software, and accessories, as well as an industry-standard operating procedure for PMI testing, specifically written for the Niton analyzer.
Our PMI training options have also set a new standard in the PMI industry with the world's only API RP 578 PMI certified training course. This 2 or 3 day course can be conducted on-site or off-site. It is provided by API-approved Analytical Training Consultants, Inc. The course includes an API RP 578 PMI certificate and ID card, which is valid for 3 years, after which a recertification is required. If you would like more information, contact your local Thermo Scientific Niton Analyzers representative or visit api578.com.
For information on new application of the XL3TS Gold technology for analysis of residual element content of carbon steels in HF units, you may view the brief presentation comprising the last part of this module. please contact your local representative for further assistance or additional information. Module 4.1, Residual Element Content. A new PMI application for the analysis of residual element content in carbon steel piping and welds has recently been developed for the Thermo Niton XL3T. This new capability is made possible with the improved detection limits now obtainable using the XL3T 900 with gold technology. Carbon steel piping and welds are utilized extensively in the HF hydrofluoric alkylation units that reside within petrochemical refineries. The Niton XL3T gold instrument can perform an in-situ analysis of 3 key residual elements found in carbon steels: copper, nickel, and chrome.
It has been determined that a combined concentration of 2,000 ppm or greater of these 3 residual elements will reduce the HF acid corrosion resistance of the carbon steel. Known as flow-accelerated corrosion, it occurs when the levels of these 3 elements are out of specification, possibly leading to catastrophic failure.
Since we have a combined LOD, limit of detection, of 600 ppm for the sum of copper plus nickel plus chrome with our high-performance Niton XL3T gold instrument, it can accurately determine whether total residual elemental content is greater than or less than 2,000 ppm. Total analysis time is 40 seconds for these elements. Even lower combined detection limits, 400 ppm, are obtained for longer analysis times, 100 seconds.
Limited sample preparation is required. The analysis area must be sanded clean prior to testing. The Niton XL3T Gold software will display both the separate analysis result for each of the residual elements as well as the combined sum of the 3. The software also has the ability to present a pass, less than 2,000 ppm, analysis in green, or a fail, greater than 2,000 ppm, analysis in red on the instrument display. Please contact Thermo Scientific Niton Analyzers Business Development Group for more information on this new application.